When we solved quadratic equations using the factored form, we started to get the sense that we were only able to solve those problems because the numbers were specifically chosen to work out nicely. With just a small adjustment to a single number, a problem might go from simple to nearly impossible. The advantage of using the vertex form, then, was that the process worked regardless of how complicated the numbers got. Sure, changing a number here or there might result in an answer that contains some combination of fractions and square roots, but we were able to get an answer nonetheless. Despite these advantages, though, you may still have noticed one particular situation that we've been avoiding when it comes to solving equations with the vertex form. Every time we've gotten to the point of taking the square root, we've had a positive number to take the square root of. So, what happens if this is not the case? Let's explore this situation further to see if our vertex form strategies really do work for any quadratic equation. We'll start things off with this equation, and as we learned in our last video, we can begin by moving all the constants to the right side of the equation. Then, since we don't have a leading coefficient to worry about, we can determine the constant that we need to make a perfect square on the left side and add that to both sides. Then, we'll rewrite the left side as a perfect square and take the square root of both sides. But what does it mean to take the square root of 0? Well, first, let's consider this separate but related equation. It's actually not too challenging to find a solution, since 0 times 0 is 0. In fact, we'll take this a step further and say that the square root of 0 is equal to 0. But is there another solution? We'll try negative 0, but since 0 is neither positive nor negative, it turns out that the negation of 0 is the same number as 0, so this isn't a separate solution. In the end, the only way for a product to be equal to 0 is if one of the numbers is 0. So a number times itself will never be 0 unless the number itself is 0. This means that this special equation only has one solution, and that solution is 0. What this means for our original equation is that we don't actually have to split it into two parts after this step, since there's only one pathway to follow. We do still need to subtract 4 from both sides, but that's easy work for us at this point. Then, we'll plug that single answer into our equation to verify that it is correct. Now, while this problem did technically involve taking the square root of a number that wasn't positive, this probably wasn't what you had in mind when we said that we would explore new cases. Sure, we now know what to do when the perfect square is equal to 0, but what about all the other numbers that aren't positive? What happens if our perfect square is equal to a negative number? This will indeed present new challenges based on our current understanding of the square root, so let's explore these challenges by considering some foundational cases. We'll start by looking at this equation, but instead of trying to solve it right away with inverse operations, let's pause and consider the question that this equation is asking. What number times itself equals -9? You might instinctively think that the answer is -3, and at first glance, that does seem like a reasonable answer. However, if we plug in -3, we'll quickly see that the left side of this equation is equal to 9 rather than -9. And if we pause and think about it a bit longer, this should make sense since -3 was a solution to this other equation that we've considered previously. Another common attempt at an answer is to just do 3 times -3, which is indeed -9. However, our goal is to find a single number that squares to -9, and whether we like it or not, 3 and -3 are very much different numbers. The problem that we're running into is that this problem is seemingly impossible. A positive number times a positive number is always positive. A negative number times a negative number is also positive, and 0 times 0 is 0. So, how in the world are we supposed to multiply a number times itself and get a negative result? The answer to that question is essentially to use math magic. We simply will the number into existence. Mathematicians have decided to call this special number I, and the defining property of I is that I times I is -1, which we can also write by saying that I squared is -1. We call I the imaginary unit, and once we introduce this imaginary unit with this property, we can start doing more complex operations with it. For example, if we take 3i times 3i, that's the same as 3 times 3 times I, which is 9 times I squared, which is 9 times -1, which is -9. And would you look at that? We just found a number that we can multiply by itself to get -9. Thus, p can be equal to 3i. But this might make you wonder if there's still going to be a second solution to this equation. So let's take a step back and try formally solving this equation. We can do so by taking the square root of both sides and then splitting the equation into two parts, one with a regular square root and the other with the negation of that square root. However, both of these equations raise a question, which is, how do we take the square root of a negative number now that we've officially introduced the imaginary unit? Well, we'll use this property, which can be summarized by saying that the square root of a negative number is the imaginary unit times the square root of the number's negation. Thus, the square root of -9 is I times the square root of 9, which is I times 3, although this would typically be written as 3 times I, or simply 3i. From there, we can replace the square root expressions in our answers with 3i, which gets us solutions of 3i and -3i. We can see that our first solution is the one that we evaluated earlier, so we know that this answer checks out. But let's evaluate the second answer as well to make sure that it also checks out. We can evaluate -3i squared by writing it as -3 times I times -3 times I, which we can rearrange this way. Then, since -3 times -3 still gives us +9, and since I times I is -1, we do indeed get -9 as a result. With this newfound imaginary unit at our disposal, let's solve a few more basic quadratic equations involving square roots of negative numbers. For our first problem, let's try w squared equals -36. We'll take the square root of both sides and split the equation into two parts accordingly. Then, we need to figure out what the square root of -36 is, and we can do so by writing that expression as I times the square root of 36. This then simplifies to 6i, and so we get solutions of 6i and -6i. Next, let's check out the even more fundamental equation of x squared equals -1. When we split up our equation here, we can simplify things pretty quickly by using our properties of the imaginary unit. This gives us solutions of I and -I. An important note to make here, though, is that I and multiples of I aren't actually positive or negative, since the terms positive and negative really only make sense in the real number system. However, we do still sometimes use these terms in combination with the imaginary unit, like when we called this answer -I. The reason for this is because -I can be thought of as -1 times I, so there is a sense of negativeness to that number. From there, let's check out these final two equations. In the first one, we end up getting these two solutions, which we can simplify by using the imaginary unit. After that, there aren't any other major changes to make since the square root of 7 doesn't simplify. You may be wondering, though, how we should write our final answers. Should we leave the I in front of the square root or place it after? We do typically place I at the end of the expressions that it appears in, but we have a stronger preference for placing square roots at the end of expressions. Thus, we'll keep our answers in this form with the I in front of the square root. Lastly, we have this equation whose solution process will start off this way. At this point, though, you may notice that the square root of 28 can still be simplified, since 28 can be written as 4 times 7. Then, we'll rearrange this simplification to this form, which gives us these two solutions. In the end, anytime an expression squared is equal to a negative number, that expression will be equal to some real number times the imaginary unit. We call these solutions imaginary numbers in order to contrast them with the real numbers. Don't let these naming conventions fool you, though. The imaginary numbers are very much an important and useful part of mathematics, with applications that get used in the real world. Now that we have at least some level of familiarity with imaginary numbers, let's use our knowledge of those numbers to solve some more complicated quadratic equations. In this example, one side of the equation is a quadratic expression that's already in the vertex form, which means that we can start by subtracting 23 from both sides. Notice then that we get an expression squared that's equal to a negative number. At this point, we know that we can still simply take the square root of both sides, but that this process will result in imaginary numbers instead of real numbers. This results in splitting our equation to get these two new equations. Then we can add 9 to both sides of both equations to get these answers. Here, you may be wondering if there's a way to simplify our answers any further. For example, maybe 9 plus 4i is just 13i, or maybe just 13. Well, both of these attempts at simplification are incorrect. The original expression represents 9 real units plus 4 imaginary units, and those two units don't mix well with each other. Thus, this is the most simplified that we can get our answer. For our next example, we're considering an equation that starts with a quadratic in the standard form. We'll also go about getting our solution in a slightly different way than we normally would. Notice that since our standard form expression was really close to a perfect square, we simply subtracted 1 from both sides of our equation to achieve a perfect square on the left side. Normally, we would have subtracted 26 from both sides and then added 25 back on, but eventually we reach a point where we can combine those steps if we want. And now that we've completed the rest of the solution process, we can see our answers here. As we mentioned before, each of our answers consists of some real units plus some imaginary units, and those two types of units can't be combined. Because of this, each of our answers looks more like a mathematical expression than a single number. Despite this appearance, though, we do actually consider each of these answers to be a single number, and we call these numbers complex numbers. A complex number is any number of the form a plus bi, where a and b are both real numbers. Since A is on its own, it's called the real part, and since B is being multiplied by I, it's called the imaginary part. Thus, for our first answer in the first problem, the real part of that answer is 9, and the imaginary part is 4. But for our second answer in the second problem, the real part is -5, and the imaginary part is -9. With this newfound knowledge in mind, let's look at a couple more examples of quadratic equations that have complex and non-real solutions. The main thing to remember here is that no matter how easy or complicated the numbers look, the solution process associated with the vertex form can stay consistent. We make sure our equations are fully expanded with all the variable terms moved to one side and all the constants moved to the other side. Then, we eliminate the quadratic coefficient by dividing the whole equation by that coefficient. After that, we add a constant to both sides to create a perfect square on one side of the equation, and from there, we can take the square root, either split the equation or use the plus or minus sign, and eliminate the final constant to see our final answers. And now that we have the realm of complex numbers available to us, we're able to access a more complete and robust system of numbers when solving quadratic equations. That concludes part 3 of this video on solving quadratic equations using the vertex form. Hope you learned something new, and thanks for watching.